Welcome to today's paper reading. Today's paper is titled, OpenHands, an open platform for AI software developers as generalist agents. This paper was published on the AR14 preprint by Xingyao, Wang and colleagues from Jiayi, CMU, and other institutions. The OpenHands platform is designed for developing AI agents that interact with the world in ways similar to human developers. These interactions include writing code, using command lines, and browsing the web. The platform supports the implementation of new agents, ensures safe interaction with sandboxed environments for code execution, and facilitates coordination between multiple agents. Additionally, it incorporates evaluation benchmarks. The platform has been evaluated over 15 challenging tasks, including software engineering and web browsing benchmarks. OpenHands is an open-source project released under the MIT license, with contributions from over 2.1K contributors. The introduction of this paper highlights the increasing capabilities of AI agents powered by large language models. These agents can perform tasks such as responding to user queries, solving math problems, and generating code. The paper introduces OpenHands, a community-driven platform designed for the development of AI agents. OpenHands features an event stream architecture for interaction, a Docker sandbox runtime environment, and multi-agent delegation. The platform has gained significant traction with 32,000 GitHub stars, over 2,100 contributions, and more than 188 contributors, positioning it as a catalyst for future research and applications. Figure 1 showcases the OpenHands user interface (UI), which provides users with the ability to view files, check executed bash commands and Python code, observe the agent's browser activity, and directly interact with the agent in real time. This interface is crucial for monitoring and controlling the agent's actions, ensuring transparency and user oversight. Figure 2 provides an overview of the OpenHands architecture, which is composed of three main components. The first component is the agent abstraction, where the community can contribute different implementations of agents into the Agent Hub. This component allows for a diverse range of agent capabilities and functionalities. The second component is the event stream, which is responsible for tracking the history of actions and observations. This ensures that all interactions and outcomes are recorded and can be reviewed. The third component is the runtime, which executes all actions and translates them into observations. This component is crucial for the actual operation of the agents within the OpenHands environment. In this section, we delve into the architecture of OpenHands, focusing on how agents are defined and implemented. An agent in OpenHands is capable of perceiving the state of its environment, which includes prior actions and observations, and producing actions for execution based on a user-specified task. The state data structure encapsulates all relevant information, with a key component being the event stream, a chronological collection of past actions and observations. OpenHands connects agents with the environment through a core set of general actions, such as IPython action for executing Python code, cmd-run action for running bash commands, and browser interactive action for web browser interactions. These actions are designed to provide a comprehensive and flexible set of primitives for various tasks. Additionally, OpenHands features an agent skills library, which is an extensible Python package designed to enhance agent capabilities. This library includes rigorously tested tools and follows specific inclusion criteria to ensure reliability and relevance. Figure 3 illustrates a minimal example of implementing an agent within the OpenHands framework. The minimal agent class includes a reset method to initialize the system message and a step method to process the current state. The step method iterates through the state's history, appending action and observation messages to generate a response using the LLM. The response is then parsed to determine and execute the appropriate action, such as running a bash command, executing Python code, or performing a browser action. The Agent Hub introduces several types of agents. The Codact agent is the default generalist agent, based on the Codact framework, capable of executing code or engaging in natural language conversations. The Browsing agent is a generalist web agent with improved observations and actions, utilizing zero-shot prompting. The GPT Swarm agent pioneers the use of optimizable graphs to unify language agent frameworks, allowing for automatic optimization of nodes and edges, which drives advancements in multi-agent systems. Table 1 provides a comprehensive comparison of various AI agent frameworks across several key features. It highlights whether each framework includes a standardized tool library, supports built-in sandbox and code execution, and provides access to a built-in web browser. Additionally, it examines the framework's capabilities for human-AI collaboration, hosting various agent implementations, offering an evaluation framework, and integrating quality control measures. In this evaluation section, the authors systematically track progress in building generalist digital agents by integrating 15 established benchmarks into OpenHands. These benchmarks span across software engineering, web browsing, and miscellaneous assistance tasks. The evaluation compares OpenHands to open-source reproducible baselines without manual prompt engineering. Key results include competitive performance in software engineering tasks such as SWBench and Muennighoff, web browsing tasks like WebArena and MiniWebB++, and miscellaneous assistance tasks including Jiayi, f.k.a, and AgentBench. The evaluation highlights the generality of OpenHands agents, which perform well across diverse task categories without specific task optimization. Table 2 presents the evaluation benchmarks integrated into OpenHands, which include 15 established benchmarks. These benchmarks are categorized into software engineering, web browsing, and miscellaneous assistance. The required capabilities for these benchmarks range from fixing GitHub issues and bugs, to text-to-SQL conversion, bioinformatics coding, machine learning coding, software API calling, and tool use. Additionally, web browsing benchmarks require goal planning and realistic browsing, while miscellaneous assistance benchmarks cover tool use, graduate-level Q&A, operating system interaction, multi-turn math and code problems, state tracking, and deductive logic reasoning. Table 3 presents selected evaluation results for OpenHands agents, highlighting their performance across various benchmarks. Notably, the Kodak agent version 1.8, utilizing Claude 3.5 Sonnet, achieves a competitive resolve rate of 26% in software engineering tasks. Additionally, the OpenHands Kodak agent demonstrates a successful bug fix rate of 79.3% in the Python subset of Muennighoff. This table underscores the agent's versatility, showing competitive performance across software development, web interaction, and miscellaneous tasks without modifications to its system prompt. Table 4 presents the evaluation results of OpenHands agents in software engineering tasks. Key highlights include the Kodak agent version 1.8 achieving a 26% success rate on the SWBench Lite, fixing 79.3% of Python bugs in Muennighoff, and a 76.47% success rate on MLbench. These results demonstrate the agent's capability in handling diverse software engineering challenges. Table 5 presents the evaluation results of OpenHands web browsing capabilities across two benchmarks, WebArena and MiniWebB++. The OH browsing agent version 1.0 demonstrates competitive success rates on both platforms, highlighting its generalist approach. In WebArena, it achieves a success rate of 34.6%, comparable to specialist models like AutoWebGLM. On MiniWebB++, the agent completes nearly half of the tasks without environment-specific adaptation, though specialist models trained with reinforcement learning and human behavior cloning show higher performance. The average cost for OH browsing agent version 1.0 on MiniWebB++ is 0.02, indicating efficient task completion. Table 6 presents the evaluation results of OpenHands agents on miscellaneous assistance tasks. Key highlights include a score of 32.1 on the Jiayi Level 1 validation set, a success rate of 57.6% on the f.k.a diamond set, and a score of 57.6% on the AgentBench OS subset. These results demonstrate the capabilities of OpenHands agents in handling diverse and complex tasks. In this conclusion, the authors introduce OpenHands, a community-driven platform designed for the development of agents that interact with the world through software interfaces. The platform offers several key features, including a powerful interaction mechanism, a safe sandboxed environment, and capabilities for multi-agent collaboration. These features are intended to accelerate both research innovations and real-world applications of agentic AI systems. Despite facing challenges in ensuring the safety and reliability of these agents, the authors express enthusiasm for the platform's vibrant community and its potential for continued evolution. Thank you for watching.